All right, what's up, everybody? Sorry we had a few Skype issues, but now if the Skype gods are with us, then we might have Jesse.
Hi, everyone.
Yay, we have Jesse. Sweet. All
Sorry
right.
about that.
That's all right.
Disastrous.
That's fine. We had to sort out audio driver issues. Maybe now that we know C, we can fix them.
Oh yeah. Well, anything would be better than the Windows kerfuffle. So.
Yes, it's very fun to deal with those kind of problems. But anyway, we're not going to talk about machine issues tonight. We're going to wrap up C as an additional language. This is the last and final course in the CaaAL series. So that's a lot of A's. And I think, did that count look good to you, Jesse? Is that?
Yeah, I think so. You should just have like an abbreviation, like A3 or something.
CA3L. Yeah, that's better.
You know?
I like that. Yeah, we'll do that. So
fancy.
We had a nice little bit of fun on the start screen. That was this is just a little bit that I've been playing with lately. This is a 10 degree of freedom sensor, which is pretty fun, inertial motion unit. So we'll probably get to that later. See. But instead, today we're mainly going to be going over the series. So this is kind of, now we're probably going to go on with some project work after this, but today it's going to be a little bit different than usual. We're not going to be doing a ton of coding because we've mostly been doing that. So we do have Jessie here, there she is, and we have our multi-user pad where we can actually like see all the wonderful things that each of us is typing when we want to compile. And if we're in luck, then this actually still runs. Yeah, good. Okay, we're getting output. So, yeah.
Tech issues have stopped.
I know, that's the problem. You know, a few tech issues, it's like, now we just gotta okay, reset. We're good. All right, we're gonna go figure that out. So, I'm going to, let's see, Jessie has the whiteboard up here. She can take a look. So let's show all of you. Now, I have not tried this out on this computer, so we're in all sorts of experiment land for tonight. So I am going to inertially move this sensor and get it out of our way. And the puns will be coming all night, don't worry. And all right, so what did we do? We had 14 sessions. Do you believe it?
Oh my gosh, are you serious? I guess, you've been keeping track, so yeah.
Yeah, this is topic 14. This is like quite a journey. I mean, you know, you made a idle comment one day like,
I want
to learn C. And here we go. We're there. We're on that journey. So what did we do? Well, that's actually our recap. So we had a lot of fun. First, we started off. Now, we assumed that we were sort of starting from a kind of Python basis. So we had some programming stuff. We weren't going over basic syntax. We were just kind of skipping right to the meat of the language. And by the way, can you see this? Is this visible enough for you? Hopefully.
Oh, yeah.
Okay, good. And chat, let me know if anything's like cutting out or if our audio is too low or, you know, I think
my audio disappears randomly.
Or if our audio disappears randomly, that would all be important information. Okay, so where do we start? Well, data types. Okay, so we went over the C data types because it actually has them. Unlike what we do in Python, we actually have to be really strong about declaring them. So unlike Python, we got to say exactly what we're using and how much, right? Mm-hmm. And what basic data types do we have in the language? There weren't really that many. Like we use a few and we sort of construct more complicated data types from them. So some of your favorites, the original data types that we dealt with?
Oh, goodness. Char.
Yeah, char. Char's wonderful.
And all of the various ints, and we learned like unsigned and signed.
Unsigned, yeah. Then we had long, and we had...
Yes.
We talked about short, but it's kind of out of favor these days.
Yeah, short didn't really come up too much. Long did here and there.
Short came up short.
Haha.
Oh, boy. Okay. What's up, Paul Blart? Mauled Cop. Good to see you. And if we talked about the sizes of these, we learned that they were kind of non-standard across time. And Care Bear stare. Nice, Nathaniel.
Hi, Nathaniel.
So, yeah, you can do a care and you can make it a bear. I don't know how to draw a bear. Give him a big nose.
Okay.
Bear-ish. Okay, so anyway, we had so we knew that these types. This was sort of our basic one, and it was typically like 8 bits, and our long was typically 32, but these days it's usually 64, and then int was sort of really non-standard, and eventually kind of aligned with long most of the time, and sometimes not, and it really depends on your architecture. But these days, again, usually 64. So this was just our convenient number size. And then we learned about the signed and unsigned versions of all of these. And we actually got into a little bit of detail about how unsigned is stored in the computer. I remember a rather deep lecture. We the beginning of tangents, really. And we talked briefly. Do you remember how we do negative numbers in computer representation?
Right. So there's a bit.
Yeah.
That's at the very, well, depending on which way you're counting from, at the very end. And it determines, it's the leftmost bit, and that determines whether or not it's negative.
Yeah, we had a sign bit. And
that's why unsigned, like, kind of gives you, how to put this? So signed integers, if I remember correctly, you kind of have less space for the positive, because you have to, like, you have to be able to have that amount negative as well, because you're using that bit for that. But if you have an unsigned integer, you kind of can use a lot more space for the positive numbers, but then you have to keep in mind, obviously, that it's unsigned, and you can't indicate a negative,
which is pretty cool. And we did originally, this was just the sign bit, and we did that sort of the old-fashioned way, and that led to an immediate problem, because what problem did this present when we wrapped it around? This is a long time ago. So
this was is this like the twos complement
yes
stuff?
That's exactly what it is.
Okay.
So there was a twos, we started twos complementing, and this, I'm not going to get into the specifics of how it happens, but basically this dealt with our problem of plus and minus 0.
Right, because of 0 the problem was 0 gets counted twice, right? And so you had to figure out a way to
This is bad, right? We don't want that, and we also want to make sure that our typical addition works. So if we add a negative to a positive, and this one's big and this one's small, then it ends up over here, and if this one's big, it ends up over here, and so on and so on. So we wanted to preserve that, and we wanted to preserve gates. So we ended up doing this kind of crazy twos complement thing. Okay, don't worry. The final exam does not include twos complementing, so that's you'll be all right for that. Any questions on basic data types?
I don't think so. We've used them so much that I've gotten a lot more comfortable.
Second nature now.
Yeah, and I mean, I told you about that that time that I was debugging something pretty complicated for work in Python, and just I was very tired, so I should probably preface that, and I literally started to declare in C fashion because I was, I never really understood what people meant, I guess, by like the shifting types or the like dynamic typing in Python. I understood it conceptually, but I never really understood why it'd be such a problem. Like, to me, it seemed like such flexibility. And then I got into this very complex problem. And when you're digging through thousands of lines of code, you need to be able to figure out what type things are. And I missed that declarative C fashion of being able to know immediately that this variable is this type, and it's going to stay that type.
You gave that up for the flexibility.
I know.
And the flexibility is nice,
so proud,
but
though, I was so tired I started writing C.
So we have a guest here, Math. Thank you for showing up. Came back, one of the new subscribers who gets the cool emotes and everything else. Use Enceladus, use MyPy. Interesting. A little bit of advice there from Nathaniel. So, all right, these were sort of the classic data types, and then of course, I got something handed to me by Last Miles, who was very, very upset in my initial stream because he thought I wasn't going to go into the new types. What were the new types? Then we sort of shook all those like classic types, which were sort of like standards mess off, and then we got to our nice new standard types. And what do they look like?
Is that like the uint
Yep,
8 stuff
exactly.
underscore? There's a T
Yeah.
in there somewhere.
Yeah,
Yeah.
and there's a T, and there's a uint, and then there's a 32T, and we can have a uint and a 64T, and then we can actually just drop the U and just have an int 64T and all this other stuff. So anyway, these types were really nice because they're super portable. They're far more portable than these other types, which are a little bit more machine dependent. So this was kind of like the machine independent data types. And that was, so we try to use that as much as possible, but obviously with original code, we're going to run into the classic types. Okay, and if you're Paul Blart, the Mauled Cop, and you're running in JavaScript, you can just declare everything as var and call it a day. Even though that's not even cool in JavaScript anymore because they moved on to like const and let and all that other nonsense. But anyway, so we're not talking about JavaScript here. We're in C land. Okay, so where do we go from there? Well, we finished up our data types and we were just sort of cruising along. Yeah, Paul Blart's not into the new age stuff. Yeah, I mean so the C new age stuff would be those new portable types. But okay, and we got into
Quick question.
Yeah.
So prior to those portable types, when types
it was insanity.
Depended on,
it was a dark time.
Okay, I was just wondering, like, would you have to have some kind of system check to figure out?
Yeah,
or
that's actually how those portable types work. They use systems checks and they sort of do it for you, so that way it's not littered all over your code and you can just kind of be clear about, I want 32 bits, I want 64 bits, and you deal with finding the type for this compiler in this system. Okay. So from there, I just quickly touched on representations. And that got a little bit into bit patterns. So we talked very briefly about that with 2's complement for negative. And we also know that when we're on the system, we're storing things in binary. And we showed the classic example of 8 bits. So our maximum value is 255 and our minimum value was 0. And we could get there by basically doing powers of 2, sort of the same way we did with base 10, right? So in this case, this is the 2 to the 0th place, and that was a terrible drawing. So that was 2 to the 0th, 2 to the 1th, 2 to the 2th, 2 to the 3rd, 2 to the 4th, and so on. So on up to the 2 to the 7th bit, and if I set all of these bits to 1, I get my maximum value, which happens to be 255. And these roll over as soon as they hit the number 2, because if I put a 2 in here, no, it's too big. So this becomes 0 and it rolls over. And that rollover math works the same as it does with base 10 numbers. So if I'm doing a 10, that's all fine. But if I go and do a 19 and I add 1 to it, I got to roll over to the next digit. So this becomes a 20. All right, so we understand this. It works the same way in binary as it does in our classic decimal. And we learned a handy notation for quickly referring to this, which was hexadecimal, which refer to 4 of these at a time. So F here being all ones and 0. Let's see. Well, this was also an F, so this was all ones. So I could write this out with 2 letters, which is a lot simpler than writing all these bits out, especially when I start getting to something that's like 32 bits or 64 bits or something like that. So, all right. Any questions on representation?
I don't think so.
Okay. Well, we dumped.
Feeling good.
Yeah, I'm feeling good too. We went through a lot of representation. So from representation, we moved on to looping, and looping is a bit different than Python. We had 3 looper operators. So do you remember what they are?
For, if, and while.
So not if.
Not if?
No, if is a conditional, so that's just if something do
I
this.
guess that's not a loop. So
there was one. These 2 are the ones that we focused almost all our times on.
Hold on. It's 4. No, there was one. It's 2 letters.
Yeah, there's
it's
a
2 words.
screwy version of this.
There's like a while,
which I told you never to use, and I'm happy you don't even remember it, because just purge that from your memory. But it is the do while loop.
Do while, that's it. Okay,
So
all right.
don't
I never would have guessed that.
don't do it. Don't
I forgot
don't
it. So
do
there-
while it. Just while and for. And we learned sort of like when these would apply. Like we used for when we're doing sort of counting kinds of things, or iterating kinds of things. And we used while when we were doing some sort of like Boolean condition, like like reading a file, for example. So just keep reading this until you hit the end of the file. Yep. And we could always use a for as a while. We could always use a while as a for. We could be as mean as we want to all the other programmers that have to manage our code base later. But we try to follow conventions and be good about when we use each one. Okay, so we did learn that scope is local. So for was a little bit different from your Python for, right? Which was kind of a for like X in Y sort of. Mm-hmm. Or whatever that said, for X in Y, kind of Python. But we're not in Python. We're doing C. And we only have one type of for loop, really, that we care about. And it was, what does it look like?
So you have 3 statements,
yep.
Separated by semicolons. And the first one is your starting condition, or your starting, I guess not condition, because it's just your starting value, good. I guess. And then there is kind of it's your like I always abbreviated it as my while condition.
Yeah.
So it's the condition that the loop will keep on looping as long as that condition is met. And then there's your how you want to iterate, whether you want to do it at the beginning of the loop or at the end of the loop.
Yeah, there's sort of what you do at each loop, right? So add 1 to it or whatever, take the next element, whatever that happens to be. So this is sort of I like to call it the iterand, but I don't think that that's a word, so don't call that. Nathaniel probably knows if that actually is a word or not. But so okay, we can do this, and you came to really like this, even though I told you that the whole design of Python was to not do this.
I know, which makes me so sad sometimes now when I'm doing like Python loops, and I like crave that extremely explicit nature, because especially when you're trying to debug something that's really complicated, it's a blessing to have everything so explicitly stated.
That's also exactly why they were fighting one exact problem with this, which is extremely common. Which, do you remember what it was? We didn't talk too much about Python language design, but I can tell you right now that we touched on it very briefly, but the main thing that they wanted to get rid of is off by 1 errors.
Okay. Right. And that's something that I ran into quite a bit.
We all do it. We all do it. This is super easy to do because you're managing the iterand, you're managing the start, you're managing the condition. And so it's very easy. It's like, do I want to be like equal to or greater than? Is the plus happening before or after the loop? Like there's all these like kind of like things that you might get wrong. And if you slip, you're 1 off. And it's just a super common problem. So basically the whole design of this was don't let you do that. So I told you it's people, by design.
Including myself. So because people were kind of too stupid to stop doing that, they decided to take away the fun tool and give you one that kind of restricts you a little bit more.
Yep. Yeah, that's basically what happened. So that's a good thing, and I don't know why Skype wants to be difficult with me.
Oh no,
but
what's going on?
No.
Okay, you can still hear.
We're all good. Okay, yeah, we've been having fun Skype issues.
It's been an adventure.
Okay, so all right, so we know what we're doing with loops. That's cool. Other than like sort of how you set them up and which of these you use, and the fact that there's this 3-part syntax, they work pretty much the same as what you were used to in Python. Okay. And you do have a while there as well. And you don't have a do while, incidentally, because they know that was crazy. Okay. So anyway, great. From there, we moved on to functions. And functions were a little different than Python. In particular, we had to be really careful about memory. And we had to be really careful about what showed up to the function, to its own scope. This is something we didn't deal with a ton in Python. It exists, but it's not as kind of strict because everything's sort of like a pointer without the pointer syntax. So modifying stuff happens only in the scope of the function, and that's where we got into stack frames. And so we drew lots of diagrams of what memory looked like with lots of lines, and we said, okay, this is the stack frame for function 1, and all right, let's call this 2, and this is function 1, and whatever. Actually, in this case, I'd have my stack growing up, which is bad. So this would be function 1, and this would be function 2. We want our stacks to grow down.
Big endian and something.
Yeah, which gets into a whole processor fight. But anyway, so and we can kind of like, say that these are stack frames. And so if I modify a variable in here, and then we talked about different calling conventions briefly. So when it's kind of cleaning the stack up, whether it's the caller or the callee's responsibility, say func1 called func2, in some language platforms, func2 is responsible for cleaning up, and some func1 was responsible for cleaning up. It's a set of conventions. And what we had to worry about was if we overflowed this stack, which is actually where we get the term stack overflow, when we sort of reach out of our frame and modify something, that could potentially be bad. So we'll get into stack smashing and whatever in sort of more advanced.
Smashing, okay.
Yeah, stack smashing is sort of a
sounds
fun
exciting.
Security.
Do I get a
technique.
hammer?
Yeah. It's called a compiler, but it's a powerful hammer. Okay, so this is sort of like, we had to be careful about what we passed forward and back. We only can return one thing.
Mm-hmm.
And that meant that whenever we had our return, either we had to jam all of our stuff in there, sort of like a dictionary, and this would be in C, this would be a struct. So I either had to jam everything in there to return, or I had to mess around with pointers. And I had to be careful with pointers that I declared locally, because if I declared a pointer here and I return it back here, this is gone when this stack frame gets cleaned up. So this is where we messed around a little bit with global, reaching outside of the stack frame. And this is also where we messed around with having func declare a pointer and pass it in, because then we can sort of modify it back. So we had a few cases of that, again, that's probably something I need to drill the heck out of you in a future class, but
probably.
But yeah, reaching outside of your stack frame is, there's techniques for doing it, but you have to be careful. Okay, so we had a few little bits of fun with that. Any questions on functions?
I don't think so.
Okay, well, that's good, because I'm going to test you later. No, I'm just kidding.
Oh no. Okay.
We're just doing a review. Okay, then after that, we got into stdio, which was our standard IO library. And there used to be a non-standard IO library, all these different platforms had. We didn't worry about that. We're using the newfangled C, newfangled as of like the 70s. so this would be that new age C that sort of came around. And in there, we learned we had sort of two sets of functions we worked with, and we broke this into two sessions. There was kind of the character and, let's say, string-oriented stuff. And then there was the kind of file-oriented stuff. And we worried a little bit about both of these in separate sessions, but, with these character things, we had stuff like how to copy, so we learned about str copy, and we learned about strlen, to get the length. We actually implemented this ourselves because we had to learn about how strings were constructed, which ended up being, if I wanted the string Jesse to be in memory, what did I have to do in C?
It's an array.
It's an array of characters. And what was special about it?
That technically, if I were to refer to it, it's a pointer to the location of the first character.
That's true. So there's my char pointer. Or I could just say that this whole thing is an array. But there was another special property we had to worry about. I'll give you a hint.
Oh, so it was another kind of like off by one error where you have to remember that there's the null byte at the end. And so when specifying enough memory for your string array, you have to remember that in terms of memory. Super important. So,
and that's actually how we implemented these different functions, was we could sort of scan through the string until we hit the null byte, and then we knew we were done. So if we had a string that wasn't null terminated, we could really get ourselves into a lot of trouble. So, because this would just sort of keep running through memory forever until it crashes, if we get lucky. Okay, so we implemented a few of those. Then we moved over to the file stuff. Do you remember some of those calls?
Yeah, this is like fgetS, fputS. This is where we introduced, I guess it's not a
How do we get an F in the first
type,
place?
but it's like, yeah, I think it's a data type file.
It is. Yeah.
And so
how do we start with one?
How do we start with one? Oh, we need no.
The first thing we need to do to get going with file stuff.
Is there a or like an include that we need?
Oh, well, yeah. I mean, it's stdio.h.
Okay. Well, you have to say, like, we used FH, I think, for file, but like...
Yeah. And what do we have to do with FH?
Well, you have to declare it.
Yeah, you declare it, so it's a file pointer. Mm-hmm. And then what do we do with it immediately?
Close it.
Well, yes, we close it, but before we close it, what do we do?
Open and close.
Yes.
Yeah,
Okay.
But you definitely were on my case about always closing it, though.
Yes, that's great that you remembered close before open. That makes me very happy. So here we would just specify our file name, and then we would have our specifier for whatever permissions we wanted. This could be, and it was the same pretty much as what you saw in Python, because they took it. There's all these different, there's appending, there's reading, there's writing, there's all this stuff.
Yeah, those were absolutely the same from Python.
Yeah,
so
Python didn't invent something totally new. I mean, they just said, oh, that makes sense, so we're going to do that. So more specific, this is actually called POSIX file semantics. Okay. But I feel free to tell you that now, because now you know how to use them. So that's might as well give you the terminology. Okay, so files were kind of fun. We mostly started off with these read, write, and append, and we were dealing with character strings, which we knew how to deal with, until we got to what?
Till we got to...
What was the other way that we could deal with files that was not
binary?
String? Yeah, exactly. So all of these had binary versions of them. Read binary, write binary, append binary. And these, we did not use the same fgetS and fputS type operations. We also had an fprintf, and there's...
Oh, fprintf, yep.
Yeah, there's actually an fscan. Anyway, so like we don't have to worry about all that stuff. But when we got to the binary world, we could not use these. So what were we using when we got to the binary world? We only had two operations.
Oh, I am not remembering.
Yeah,
hold on.
a while ago. That's why we're doing a review session.
Okay. Yeah, I'm shaking the cobwebs out. I think if I can.
I promised you a review, so.
Okay, how do we? So.
Well, it's not a huge mystery. I'm going to tell you that there's only really two operations you can do to a file anyway. I mean, it's referred to as
read
file
and write.
IO. Right, yeah, it's read and write. So that's it. So there was fread and fwrite.
Oh, yeah, okay.
And they basically, unlike this other stuff, which we were dealing with, where we could sort of assume that there were string semantics, these did not. And what do we have to do to deal with that?
Is this no? Because that was, I think we had to, no, I think it was fread and fwrite, where we have to specify the unit of memory and then how many units we want to read, right?
Yep.
So you have to be very explicit about how much you want to read and what the units are.
Yep. We had to say how much. We had to say what the unit was. We said where, and we said what else did we? Well, I mean, we said which file to work on. Mm-hmm. Yep. And then we needed one more thing in general, which was...
Okay, so I'm remembering. Hold on, because I remember the file handle goes last.
Yep.
And then there was... No.
Yeah.
Because there was... Let me see. So it was... I just was seeing it in my head for a second.
Yeah.
Right, and then what was first, right? Because the second thing was
what was first?
The size of a unit. The third thing was the number of units. The fourth thing was a pointer.
Yeah, it was a pointer.
Oh,
For
to
what?
what? Um,
It was actually the introduction of a new type for us.
oh no. I'm drawing a blank,
It's
honestly.
the first time
on
we
what-
saw the void pointer.
The void
Right,
pointer!
which was said this was just a block of memory.
It's my Cthulhu
This
pointer.
we usually refer to this as a buffer of some sort, and this was strange because void was basic. And at that time, you yelled at me because you said no. Void is what you put in a function to say that there's no parameters there, and I said that's true. That's true. Well, turns out void has one more use, and that's when we need to say that there's memory, but we're not saying anything about its semantics, and that was super important. So whenever we're doing void pointer type operations, we're intentionally not saying what type of memory this is.
I'll be honest, I still struggle with that a little bit. And like, I joke or like earlier saying it's like a Cthulhu pointer, but it feels very sort of like nebulous and Lovecraftian and dark magic and like
it does use the word void, so
summons ancient evil.
Yes, it comes from the void.
Okay. So I mean, it's part the name, part just it makes me a little uncomfortable, just because I think part of what I liked so much about pointers and also about how explicit C is that you always have to know kind of how much memory you're going to be using or how much memory you're going to be pointing at. And so void pointers seem to just kind of be like, nah, now we're breaking the rules. And so that, I guess I'm still sort of mentally struggling with.
But what other thing could we specify for the buffer? I mean, anything else we pick imposes semantics on our read and write function.
Yeah.
So we didn't really have a choice, right?
So why do you need a void pointer there, though?
Because we're not saying what type this needs to be.
But we are being explicit still about the memory because we're specifying the unit of memory and the number of them, right?
Yep.
Okay, all right. So it's just that we don't want to put a name.
We're passing along the semantics. We're basically saying we're going to tell you how much and how long and whatever, but we're not telling you what it is. It's an obscure detail. It's opaque. So basically,
but returning a void still is weird.
Well, it's just not giving you any rules. I mean, it's just basically saying that's like.
But come on, C is all about liking rules.
Well, I mean, if we wanted to add semantics to it, we had to actually do what? Which we actually did.
Because we wanted semantics to what?
Like when we got our void pointer out, we couldn't just use the void pointer. We had to do something to it.
What?
When we got our void pointer out.
We gotta say it slow. All right.
We can't just operate on the void pointer directly. I mean, we
No. You are you talking about the AND operator? So you get whatever it's pointing at?
Yeah. Well, we could dereference it, the star operator, but no. What I'm talking about is that we actually had to take this and move it into a different data type. So we had to give it semantics.
Casting.
Exactly. So as soon as we learned about this, we also learned about the cast. And this was really important because we need to be able to say, okay, this is actually character data, or this is really int data, or this is some arbitrary structure data.
Is that what's going on under the hood with Python's dynamic types? Is it just a lot of casting?
Kind of. It's just a little bit more complicated. But yes, like that is in general sort of the idea.
Okay.
Or you can just dereference the void pointer straight into the void, as the Ronin says. Okay, so we learned a lot, actually, which was just sort of on the side when we got to binary files. And there was something else about them that you really didn't like.
Oh, no.
And you got angry at me about it.
Oh, no.
But
okay.
I was telling you, like, okay, you can just read and write. And you just read and write however you want to these things. And then Loafbone came in your room.
Hi. Oh, thank you. It's dinner. I'm sorry.
That's all right.
Oh, okay. That was that. Thank you.
Just don't touch her cable because she...
Don't touch the cable. Like, the world will end.
The world will end. Okay.
All right. So I got angry at you about fread and write.
Yep. Because...
I don't remember.
They did not specify the format of the file.
Oh, right. So like file extensions, you just don't use them.
Well, you do use them. You make them up. This is actually how they're made up. You decide on your own set of conventions. The data is not necessarily self-describing. So that was kind of the important takeaway, and that made you kind of ticked.
It just seems like I get that if you think about it, it's like you have to specify it. So yes, it's very C-like, but at first it seemed very un-C-like because C is so like you have to specify all the things. You have to be explicit about every little detail. And so it surprised me that wasn't.
Yeah, I mean, we said that you could go into different formats that were self-describing, and a lot of formats were not self-describing. Okay, so from there, we moved on because that led us very naturally into structs. And when we got to a struct was what?
It's kind of like a dictionary, kind of like an object, a little bit of both, I guess. But it's kind of a way of storing and organizing related data.
Yeah.
Okay.
I like that. That's a good way of putting it. Organizing related data. And how do we build one up?
Struct.
Yeah.
You declare it.
Yeah, we declare what our structure type is. So it could be like a planet was the example that we did.
Yeah, we used planet.
And then we said that this has what in it?
So I think we used like orbital period and radius, mass?
Name.
Name, okay.
And we went simple. We kept it fixed size. So we said like, okay, name is like 20 and orbital period. And this was like a float and this was like a char. Well, I mean, it's just an array. And then that was the definition of our structure. And then we knew that when we declared something, we could say struct planet Bob. How do we assign to the different parts of it?
The dot or period operator.
So,
like
out.
Bob dot name
equals
Bob.
Oh wait, can you assign that to a char array?
How do we do that?
Yeah. We got by with a little help from our standard IO.
Did we just use like the brackets with
nothing? I mean, we the first one we did, we could do it one at a time. We could do a character at a time and say Bob.
Yeah, I remember doing that, but I remember there being like some fancy other easier way to do it. Oh
yeah, there was definitely a fancy other easier way to do it, but because doing this is a lot of writing and it's pretty annoying, and this is A and this is, even if I pick the shortest planet, this is a lot of work.
It's still a pain, yeah.
Okay, so we used the str copy.
Oh, okay.
And we just specified that bob.name was going to get like Mars. And we had to be careful that we remembered that this had that. And we learned something else about structs, which is that they sometimes get padded. And this occasionally screwed us up when we started talking about writing files. So
I'm thinking about how much memory we would need.
Yeah, we had to be careful about something like padding, because padding would make the CPU faster, but it also would burn bytes.
There was a way to specify to get rid of the to make sure that there wasn't padding. I don't remember the exact syntax, but I do remember that we could do that.
Yeah, there's attributes. Anyway, I'm not looking for that level of specificity. Don't worry. You can look that up if you need to. Okay, but it was important when we were talking about serializing data and storing it somewhere. Okay, so from there we moved on, and we also sometimes had to deal with a pointer to one of these things. Mm-hmm. And that would be something like, current planet. Planet. And when we were doing this, we could say we had to do a reference, because we needed the address to be able to put it into a pointer. So we would say this gets and Bob, and that would assign it up. And then when we wanted to access it with the pointer, how did we do that?
So there's two ways, but I like the pew pew operator.
Use the pew pew operator.
Yeah.
Okay, so we like the pew pew operator, so we're using the pew pew operator. So we could go, if we want to get the orbital period, we could do curplanet what?
And then let's see. You use, let me see if I can remember how to do this. Use the pew pew operator,
Yep.
and then like current planet. So and Bob. So Bob dot name or something.
Well, I mean, you
Right?
have Bob, so like, yeah, you could take name. Because
Or name,
curplanet
yeah.
is already pointing to Bob.
Right.
Okay. And we had the reverse that we didn't really do this with structs, but we knew that if we needed to dereference a pointer and like get the thing that it pointed to, we could do something like this. It would throw a star in front of it. Okay. So we had a gentle introduction to pointers at that point. And it they weren't as bad as they seemed until we got to the next topic, which was dynamic memory. Something you just take for granted in Python, and that's actually part of why it's so wonderful. So what happened when we went to dynamic memory? We had two operators that we had to deal with.
Is this malloc
Yep.
and calloc?
Yeah. Well,
Chonk alloc.
don't worry about calloc. Calloc is in there. It's sort of like a array malloc. But when we malloc something, what do we have to do to it?
Oh, free.
Yeah, that's focus on these two. Don't worry about that one because you can always just multiply this out and get the same thing. Okay, but yeah, this is important. And then what we did was we basically dealt with this in the first session. We actually did the dynamic memory allocations using malloc and free. And then because we really wanted to hit the concept home, we did the
Chonk
chonk
alloc. And that's our team chonk.
And this was the session on bring your own allocator. And we built an allocator that never gave back memory. So we made free a no-op, and we made free. And we just said malloc is going to be chonk alloc. And we just kept on dishing out memory. And this is where we started using the void pointer for real. Because now we don't know the semantics of the memory. That's kind of up to the programmer. Okay. So that was kind of complicated. And of course, when we did all this, we hit our first memory leak.
I remember that.
And I was so proud. But something you can't actually do in Python. It's not really, the language doesn't permit it, but C absolutely does. And we leaked memory like a champ, and there was no warning and no nothing. And so what we could do is go back and build a better version of chonk alloc that could track memory allocations and deallocations. So you just have to do the bookkeeping. Mm-hmm. There isn't really another way to do it. There's tools that will help you with that. I mentioned one briefly, which is called Valgrind. It's a great tool. There's other ways to do this, but this is sort of advanced stuff. It's not really part of the language. Okay. We could do it on our own when we were building our own allocator, and some allocators actually give you those options to work with. So, and there we took on the scariest topic in C, because everything's easy after that, right?
What's the scariest topic in C?
I mean, memory allocation.
Oh, but see, it's just under this beautiful haze of chonk. So it's a positive, wonderful memory for me.
There you go.
It's all about chonk.
Well, that
chonk.
brought us to the last major part of the language, which was bitwise operators.
Oh, right. Okay. That's more fresh in my memory.
And, well, now we're back into recent history. So, bitwise operators, what did these do?
So these are a series, I would say, like logical operators, kind of, that operate on a bit-by-bit level instead of a decimal addition, subtraction, or whatever.
Exactly. And they were the same as the sort of conditional versions of them, in the sense that there was an and, there was an or, there was a not, there was a
XOR.
And there was an XOR, which was the exclusive version of that. And this just basically did it on a bit by bit basis. So if you had 2 bit patterns in memory, you could piece by piece do these logical operators and determine their result, and we could do truth tables, and we started doing that.
Hashes were in there too somewhere before
no,
Bitwise, wasn't it? No, was that after?
Nope,
I'm sorry. Okay. I'm getting really excited.
I know. We're almost there. I
thought that happened before, so you have no sense of time.
That's okay. And then we could do whatever operator and spell it out. So that was fun. That also brought in a related topic, which was bit shifting. So we had...
Right. Oh, This was weird. This felt uncomfortable. It made sense, but it was weird.
We could take all the bits and we could just tell them to slide.
Right. It's kind of how CCDs work. I remember thinking that.
Go and it there. All right, so we could shift right, we could shift left, and all sorts of other fun stuff. Okay, so questions on Bitwise?
We just did that, so actually that's really fresh in my head.
It's super fresh, and it was really handy for the next topic, which was we began... I know you want to get excited, but don't get too excited, because first
I'll keep myself under control.
First we had to go through one intermediate step, which was the final section, which was the missing parts. And here we broke this into 3 subunits, and the missing parts was really about stuff that isn't directly the language, but sort of like hard to get by in the language without it. So, and I'm going to ask about that song in a second, but so the missing parts I broke into 3 categories. We had hashes, we had sorts,
right,
and we had random numbers. Let's just call this section entropy in general, because we got into both pseudo random number generation and we got into true random number generation, the really true sense of entropy. Okay, so hashes, we did a few, right? What was our first hash?
Oh, what was our first hash?
We actually used the length of the word.
Oh, that's right.
Yeah, it wasn't a very good hash. So, so we have things like word length. We have things like, we could add all the numbers up. We could add them up and stir it a little bit. By the way, you'll notice I'm borrowing the word stir from entropy because these are all related fields. So we could be a stirrer. And then we actually quickly did DJB, which is DJB2, which is a very useful hash, but not something you're expected to memorize. It was basically just kind of a couple shifts and a few logical operators and some prime numbers in there. All right. And we never explained why. Sorts. We did a couple sorts you implemented on stream. You remember them?
Oh, not the Q one. We didn't do the Q
sort. We did not do the Q one. We used the Q one, but we didn't implement it.
There was like the... Oh,
this is the one you don't use in an interview.
Sounded similar.
I'm going to call this the line of interview. And make sure that Q sort is always on the other side of the line. Do not cross the line if you don't have to. So the 2 that I said that if you're ever under the gun, you should never use them in real production code, but they're not too bad to implement. And you nailed both of them.
I swear, like one was like a reference sort and one was like an assigning sort. Insert.
Yeah,
that's one.
Insertion sort.
And they had such similar names, and I remember getting them. Selection, thank you.
Okay, and they were both sort of variants of kind of the same idea. So we implemented them from scratch. This is kind of, by the way, this is sort of one of the topics of the more advanced course. So this is after we get into data structures, we really start getting to hashing and sorting. And that's really kind of the general topic of computer science. But the last one was also equally, probably more important these days, especially with security, and that was entropy. And we talked about 2 types of entropy. Do you remember them?
Oh, physics brain is taking over. I'm sorry, computer science entropy.
Well, let's talk about random numbers then.
Oh, well, we talked about pseudo-random numbers and actual random numbers.
So there were pseudo-random numbers and there were true random number generators. And actually, this isn't really a generator. This is kind of a misnomer because you don't generate true randomness. Yeah, you harvest.
Measure it. Yeah.
And we can go harvesting true random numbers. Going. We'll get into entropy a little bit more after this. But so with pseudo random number generator, what was our goal? there was a bunch of standards, and we didn't have to worry too much about the direct standard. But we weren't going to, we were worried about what they were sort of testing for in the standard. And
we didn't want it to be easy, and we didn't want it to be
easy. Actually, that's really all of it is not easy. And we broke down what not easy means. We don't want it to be
to be able to like backwards.
Yeah, we don't want backwards and we don't want forwards. Like, we don't want it to be predictable.
Yes, that was it, predictable.
And we don't want to be able to recover it, right? You know, we don't
want it to be obvious.
Yeah, we don't want it to be recurrent. So, and we also want to sort of hide the state for where we did it, and so that's where hashing came in. So we could use hashing
and
to
random
sort of
seed.
Yeah.
Yep.
And then we would also hide our seed and, you know, whatever else we wanted. Okay, but
I got to be the most troll-like that I've been so far. That was really fun.
Yeah, super fun. True random numbers, where did we find them?
So that's like, it has to be a phenomenon that you kind of observe.
Yeah, it's usually something physical.
Mm-hmm.
And that's really important because pseudo-random, a computer is a very ordered device. It's always trying to reproduce exactly the same results for the same input. So
there's like that entropy or
the war.
True random number generator
that
like you said like the NSA uses or something, and it's in your computer and you should never use it.
Yeah, that's the RD-RAND instruction.
There we go. Yeah, I forgot exactly what it was, but
so I was like, we busted to some inline assembly for that one, but there was actually a much better place where you could get randomness from, and that was about collecting all of the environmental noise sort of on a machine. And I don't know if you remember or not, but this was the dev random device.
Yes.
And we actually read a few bytes from it. We could just use normal binary operators on it. We could just open it up and kind of get to work, and we were good to go. So, that's a lot of stuff.
Yeah.
Okay. Yeah, we actually, as Paul Blart just mentioned, our first random generator was the Randall Monroe. And we checked how to spell Randall Monroe's name. But there was the Randall Monroe number generator, which was just return 4.
4, yeah.
Okay, so
that's where we started.
We actually started right there. So that, in a nutshell, is C. How do you feel about that? I mean, there was basically, that was all of it. That was the entire language. I left one or two obscure details out. They're not super important, other than the other one that we're going to talk about today, which is actually the last little bit of new content. And it's really just a teaser because we're not really going to get into it. So,
I'll say what I said in an interview. I had a job interview today, and I basically said that I've learned a lot of C, but I would not call myself a C developer in any sense. Like, I feel like...
Go ahead, do some C development. You got the console right there.
Oh, Lord. No. So I was like, because they were asking me about what languages I'm familiar with and what I feel comfortable doing. And I was, I'm learning C, but, you know, don't ask me to write any.
I would say that the biggest thing that you're missing in C is just practice. It's not that there actually isn't any more C other than there's some technique you'll pick up, but there's nothing else in the language. It's really, at this point, it's really about making everything that I just talked about has to be second nature. And that really comes from like doing assignments, and I never had this, that I take the blame for that more than you.
Homework.
Yeah, you didn't have any homework. And that's actually kind of like the part that would really internalize it for you. Like that I think is the biggest missing piece from this class. Mm-hmm. But that if this tool was in a state where I felt comfortable leaving it online, then we would be good. But it still has the warning glaring security hole on the website. Okay, so that actually, if we look at our learn, that's the whole class. So we did all of it. We had some data to play with, but you know, that was. I actually developed a vocabulary we didn't use. So I have 1,000-word astronomy vocabulary that I'll probably just post on the website. But that's a whole separate thing. So anyway, I mean, aside from practice, which you pointed at, right? So obviously, like, you need some practice in C. I think you can't just do it once and say you know it, right? So
absolutely.
That were there any like parts of the language that, I mean, we didn't get into function pointers too much. We did actually use them
conceptually.
Well, no, we actually used one in QSort. So with QSort, we actually had to specify a function that it would call to compare two numbers.
We didn't build QSort though.
We didn't build it, but we used it.
Okay. Yes.
So that actually does have a function pointer in it, but we didn't spend much time with it. I mean, that's just kind of like you can pass a reference to a function in and say, have fun. So radioactive materials, by the way, math, those are a nice source. Cosmic dust, there's everything astronomy related.
And images, I honestly think would be a great source.
It's fantastic source.
Well, I got infinite amounts of that. So
yeah, things that you can hook up to a analog digital converter are usually pretty good. So like I mentioned, a detuned FM radio. Hey, what's up, Jane? So there's all sorts. Yeah, Twitch chat alone is probably a fantastic source to harvest. So we've got all the randomness we need right here. So so that was kind of like in a nutshell. Those are the major topics to see. So did you have any questions about any of those?
Not off the top of my head.
Which is fine.
Because usually I just peppered you with questions when we were learning it.
More that way too. I mean, so then if it comes up, feel free to continue peppering. So anyway, so for the last piece, there's something that we've been using all along and we never got to talk about. And I think that that's a good spot to end our language study for the intro course. And again, intro in the you already know another programming language. I think this is totally inappropriate as like a first-time programming course. So the first piece was this, and I never really explained it. We just started using include, and we didn't really talk about what it meant. It was a reference to, like, if we include something, then some more functionality came in. And so we included things like stdio, and we got stuff. When we included it, we got things like strcopy and strlen.
I thought of it like a Python library.
Yeah.
I know that's probably okay. That's
right.
Okay.
It sort of is. And we also, when we included standard int, we got stuff like uint at and all that other thing. There's more here, right? We can include math.
Sorry, math. Just all of math.
We're just I meant math. So anyway, so no, you can include all of math.
Is there anything that's not .h?
H means header, so includes are almost always .h.
Okay.
That changes when you get to C++, but for C, it's almost always .h. Okay, and so we can include, and this was kind of, we learned it as sort of a way of bringing in functionality. I kind of lied a little bit. That's not the whole truth. So we did touch on it briefly when we looked at the heap, when we actually did the exercise where we looked at heap allocations and we were like, kind of looking at proc self maps. But there was I told you there was this sort of like, there was sort of the stack growing down and there was the heap growing up. And then in the middle, there was sort of this like area you should never cross.
Yes.
And that was important, right? One does not go to Mordor. Okay, so like that little middle area.
Don't cross the stream.
Yeah, don't cross the streams. This was our library load. So this was our shared library stuff. And that's actually, this stuff, the H files, really just bring in the definitions of what functions are in there. But they're not the functions themselves. So we didn't actually kind of do that. But like, so for example, when we built the function like...
So they're just pointers to the functions, or...
Well, sort of. So they're actually just the definition of the function. So if I say something like uint 32t Randall Monroe random and this took nothing in and it returned like 4. Okay, this is a full function, and this is the way that we typically specified functions when we were programming. Well, it turns out that you don't need that if it's from another file. So
Okay.
Or
so
actually,
it's
what you can
just
do,
like normal. I mean,
well,
kind of
what you
software
really
development, right? You
need,
don't want it all in one file.
yes, but what you really need is how this works, this part that I selected. C needs that to be able to kind of say like what this function's, how to link it up, how the stack's
Okay.
going to work and everything else. But it doesn't really need to know how it works until you're actually linking the final executable. And I know I'm hand waving on link, but like if I have different like chunks of code and I want to sort of like link them all together, like maybe different programmers are working on different things, or somebody's building a math library, or somebody's building, say, the fastest Fourier transform in the West, which is a real thing, and it is really fast. Someone comes along and does something like that. You don't really need to know the implementation details to be able to call it. All you need to know is how to call it. And that's what we call the definition. So you don't need the implementation, which, by the way, is incredibly magical. This is the implementation part down here. It's a very, very complicated function I picked. But we actually, all you need to do to be able to call this thing is you just need the definition of it. And that's actually the definition, which is to say that this takes no parameters in, and it returns a uint32t.
Okay.
So C only needs this when it's compiling. It needs this sort of when it's linking.
So, okay. What that sounds like to me is that it needs to know, like, from a memory perspective, when you're compiling, all you need to know is what it's going to return and what it's going to take.
Yep.
And then when you're linking, you need to know all of the other possible variables and whatnot that you're going to
Well, you need the actual concrete code.
So is that like a heap stack distinction?
No.
Or?
You need the concrete code.
Yeah.
Right. So, like, in the first one, you're sort of saying what it takes and what it returns. Mm-hmm. And in the other one, you're saying this is actually how to do it. This is what to run on the computer. So those two can be separated. Right. So this is actually the definition where I'm just specifying this is how to call this function. But here I'm actually giving you the concrete implementation as well. Mm-hmm. So that's kind of the difference right there. So this is sort of like the protocol. I'm overloading the use of the word protocol. This is sort of like, this is how you greet this function. This is how it gives you back a response. But you don't actually know how this thing works just looking at the definition. Right? If I don't show you the function, this is actually enough to compile.
What? I understand based on the definitions you've given me, yes, but that just...
No, I mean, that's it. I mean, I can just, from this, I can say, all right, take a uint32t and call this some number, and then assign that a Randall Monroe random number. That's enough for C to be able to build this unit. Like, it knows that it's going to eventually need to find this function, but it knows already how that function looks in terms of like calling it. Mm-hmm. That's it. That's actually the difference. So this is just enough information to be able to call it, but it's not enough information to be able to execute it.
Okay. So is the hashtag include thing, is that just somehow shorthand for what you've highlighted there, but for all of the definitions?
Header files are usually just definitions. Okay. So it's just the definition of all the functions that are going to be in there, but not the details of how to do it.
How does it know how to get the details of
this is not really C. So this is kind of more of like build systems and linkers and stuff like that. Like this gets kind of out of the... I mean, it's clearly related to the realm of C, but it's not actually the C language itself. So the important thing to take away is that you can split up the implementation from the definition of it.
Okay.
And this is basically how to do it. So these header files, that's the part I wasn't entirely honest about. These header files, they have mostly definitions.
Okay.
How does pound include work? Well, it actually is a lot dumber than you think. It's nothing like the Python import. Import implies in the name that it actually does some stuff, right? Like it imports this
Yeah.
module, right? Like it's bringing it into existence and it's initializing it and doing other wondrous things that we don't need to know about. But include actually literally means paste this text file right here.
I was wondering.
Like,
okay.
Take this text file and paste it right here, and that's it. That's actually how this was the first preprocessor directive. So this means before you go compiling this thing, first find this file and just paste it right here. Where do you paste it? Exactly where it is on this line. So paste FFTW right here, paste math.h right here, paste standard int right here, if I reverse the orders, these are not the same. This is a different program because this actually says paste stdio right here after standard int. And by the way, that will sometimes cause your code to break because sometimes these things depend on different. Yeah. So you actually have to be really careful of that. It is really dumb. It just copies and pastes. That's it. It does no thinking. Like this whole import thing, this is a much more glorious term, right? It sort of, it's like, I might initialize something, I might run something, I might contact a developer, or I might run a neural network while you don't know. I mean, like this could do basically anything you want. It could capture variables, it could do whatever. This thing is literal. It does not do anything other than it pulls that file in and slaps it right there in the text.
Okay.
And Nathaniel is absolutely right. It's kind of beautiful in how simple it was, and it's also terrible in how simple it was because that actually caused all sorts of trouble that we learned about later. But so that was kind of like, that's the beginning of the preprocessor. There's one,
like every code I've ever written. It's
super important with C. C is such an early language, so like a lot of development, we were sort of learning like what bad ideas were. And there's a lot of opinions. Those opinions are now called programming languages because those opinions have been followed for a long time. Okay, so there's one other preprocessor directive we're not going to get too into, but it's called define.
I've seen that. Okay. When I did a co-stream with Last Miles, and we were working on, actually we were practicing hashes after the hash lesson that we did. And so I was I was watching him do stuff, and define came in quite a bit, and it seemed like it was you're defining variables of a sort, but I wasn't sure if it was like
they're not
variables or
again. The hint here is the fact that it has a pound in front of it. Pound signifies
you're gonna copy paste something.
Yeah, not necessarily. It means the preprocessor handles it. The language doesn't.
Okay.
So it's not. It's part of the language, but it's kind of not, right? You could actually build a C implementation that doesn't do this at all. In fact, early C compilers, the preprocessor was a separate program from the actual like compiler. Yeah, these were usually like M4. Or, there were different macro packages that were responsible for this. Define does not create a variable. That would actually involve like building storage and stuff like that. Define literally means, when you see this, put that.
Okay.
And that's it.
So an alias, kind of.
It kind of, except it's really literal. Like if you come along and you say like, printf, this was pretty cool.
Even in like, okay.
It has no knowledge of the language. Okay, it's handled by the preprocessor. It is not handled by the language. So that's important. Okay. It's that specific. Okay,
I feel like there could be some danger. Like with the find and replace snafus.
There's huge danger. This allows you to write the worst C imaginable. You could say things like, define main to be not main. And this program will fail from now on.
Oh.
You could say pound define int to be float. So every time you actually get an int, it'll actually turn it into a float. This thing is a really dangerous tool. So like there's a reason I did not really mention it in the course. That
also feels like another way to just obfuscate your code a little more.
The obfuscated C contest is normally won by some really crazy defines. So there is sort of like a good and best practice to define. One of the things is like, well, don't And actually, that kind of speaks to what you were talking about earlier. Like, how did they do something like uint 8t? Well, they did something sort of like if you're on if defined risk platform, risk 5 platform, then, and by the way, there's some more stuff that I wasn't talking about in the preprocessor. But
I can see that.
You could say things like, all right, then type def, which is something else we didn't talk about, uint 8t, all these dark side components, like they're dangerous. Okay, so I don't feel comfortable talking about them in the the basic intro to C course. Like this really, like, for now, try not to do anything with the preprocessor. That's like focus more on the language. If you're reaching for the preprocessor, don't reach for the preprocessor.
Okay.
Okay. There's actually, as Matt just mentioned, there's actually a warning. This code shouldn't run. And by the way, when you compile this, like, we don't have FFTW installed, so if we get that warning. Like, just when you compile this thing, it will tell the person compiling it, by the way, just to let you know, like, don't change this value.
It's really cranky at the apostrophe, so I might take out the apostrophe.
Don't, like, you can do all sorts of fun stuff. We could actually fix this. We could quote it if we want. It sort of depends on, like, but you're now you'll notice that main is not defined anymore. What happened to main?
Oh, because of
I warned you.
I forgot you did that. Okay.
That's
vicious. Right.
And where that gets really crazy is when you do it in one of these includes, so the programmer doesn't even see it.
That just seems like you're being a jerk.
There's reasons. Okay. We're not going to get into the wonders and the horrors of the preprocessor. Their own is kind of giving you a taste of the dark side. Just stay away.
Okay.
Just don't do it. Okay. So anyway, you should know that it's out there. Yes. It's not really the basic C stuff.
To be perfectly honest with you, this feels like the conversation that my parents had with me in middle school about drugs.
Yeah.
Like, we want you to know they're out there, but we don't want we don't want you to use them.
I feel like that's the only way you can end a C course. It's like, okay, now you have the kung fu.
Is this the gateway drug?
You have the kung fu. You need to be never use the killing technique. Okay, like this is dangerous stuff here. Okay, so it is our last conversation on basic C. So, anyway, and by the way, you can turn off warnings. There's ways to turn warnings off, but I'm not going to show you that either. Okay, so that's just the last thing, and that gets a little bit into how multi-file support works. In C, it actually was sort of bolted on because originally you just wrote everything in like one program, and then when you started wanting to have multiple files, that's when somebody came up with this preprocessor, and they said, "Oh, I'll just take that file and include it right here," and that's how it happened. So we still deal with it. That's life. All right. When we compile things, we do have to worry about compiling units and getting them to work together and whether they were compiled by us. Sometimes we get code from a corporation, say it's commercial code, and they will not tell you the implementation. They will not ship it to you. They'll say, no, that's our trade secret. We'll give you the library and we'll give you a header file so that you can call it. But we're not going to tell you, we're not going to give you the code because that's a trade secret.
And wait, how?
It's just that the language grew up in that era. You could get this special library. We're still there to this day. Most of the time it's hidden in firmware blobs these days. But like or like a Wi-Fi driver, or say like a video card GPU driver that's 500 megabytes and big enough to say have an entire operating system in it, including multiple compilers or whatever else is in their NVIDIA. But so not getting into that, but like we don't always get the implementation. Sometimes we actually just get a library. Sometimes we get a linked it depends on the link format. Mm-hmm. It's not the actual executable, but they'll give you the linked unit, like this is the linker object. There's different ways. These days, it's usually a shared library. So they'll just give you a shared library and they'll say, we're not going to tell you how to compile this thing. We're not even going to show you how it works, but here's your definitions and you can call into it. Well, that's the real life of a C programmer. Sometimes there's actually really good reasons for being opaque. Like, I'll tell you one of the best is...
I mean, trade secrets, I understand.
No, not trade secrets. That one almost always backfires. It's almost always a bad idea. It's usually better to, like, be on a shared source type agreement. But so one of the ways that usually is useful, say if you're in a team and it's not your responsibility. Like, say somebody has to build, like, a good Fourier transform implementation. Okay. And that team just sits around building the best Fourier transform or the best like JPEG decoder for ARM or the best like, so say like there's like, this type of specialization across a really large organization. Then you usually don't care how they do it. So in a sense, you can look at the code because usually you have access to the same code, but you kind of don't care. You as the programmer, it's your job to consume that API. So you're basically just saying, look, I'm calling your functions and they don't work or they do work. So like, it's kind of like the details are opaque to me. I don't care how you decode the JPEG. I care that you do a good job. And that allows that type of boundary between teams and orgs, and it can go across companies and whatever. So there actually are like reasonable, like let people worry about their specific like areas. So like you can have a team that's like their specialty is just building ridiculously fast like recurrent neural networks. And you don't really care. You care that the interface doesn't change, right? Because that's how you're going to call it. But
I guess. I don't know. I've had way too much experience with bad code getting packaged and lauded as good code that I'm very nosy now.
Well, that's part of it is like, why do you care about the implementation detail? Because that means something went wrong.
Yeah.
We call that a leaky abstraction. So like, you never saw the code for printf, and did you ever care?
No, I guess.
Why?
Once you get to a certain level, though, I think that it becomes necessary.
I'm not sure
to know the details.
The reason I don't care how printf is written is that I don't care how printf is written.
I get that. I'm saying that, like, especially thinking of AI and machine learning, that dangerous things happen when people hand wave and say it works, and so I don't need to understand the details. Like,
well,
that's where stuff goes very bad.
Yeah, but see, that isn't like printf. Why do we trust printf?
Well, because I think it's a lot simpler.
Not just as actually, printf is incredibly complicated.
It's not simpler not simpler in its guts, but its execution can be very easily verified. And
no, actually, it's really hard to verify
printed.
It. There's certain organizations that won't let you use it because it's a variadic operator and it causes so that's actually printf is phenomenally complicated, by the way.
Okay.
But the thing is, we trust it because it's rock solid. There's been tons of years of engineering on it. There's there's a whole world of like good printf and bad printf. There's conformance tests. There's all sorts of like standards that say that this printf is functioning correctly and this one is not.
Yeah, exactly.
So it's very evolved code, and in a sense that's great for us because from a point of abstraction we don't care how it works. We just want to get some other task done, and we want to occasionally look at some output that's formatted.
Right. I still think that once you get to, I guess if you don't want to talk about complexity, then I would say when the further away you get from something that is standardized, the more I think you should scrutinize it. And that's just because in my experience, I've seen a lot of problems happen when people just sort of take it on faith that something works because it works and it seems to be working, and we've run some tests and it says it's accurate and it's giving us the answers we expect, or oh, this team built it, so we're just going to start using it. And I find that like the lack of like the unwillingness to look under the hood gets dangerous. And I'm not saying you need to like go down to the level of every single function. You need to know exactly,
well, like Nathaniel just mentioned, you can stop the processor, you can look at the assembly. It's always there.
I mean, that's a level of I get your point. I think there is a distinction though where you leave the realm of kind of maybe it's the standards, or I'm not sure, but there definitely is a boundary to that, and it can get really messy when you cross that boundary, because I feel like that.
Could I summarize your thought in different words for a moment?
Sure. Yeah.
Could I say that given enough eyes, all bugs are shallow?
Sure. I kind of like that.
Yeah, I mean, if we say inspected a lot of the code and had a lot of smart people looking at the code and it was very transparent, then we could start to believe that, like, there's not a lot of bugs in there. We can deal with all those bugs, and eventually we'll get pretty reliable code.
I think there's like kind of hallmarks of.
Wait, before you tell me about the hallmarks, what do you think of that quote?
What, that you have enough people look at something?
Given enough eyes, all bugs are shallow.
I think that on the surface, it sounds nice. It makes me worried because there's been plenty of things that have passed peer review that have been egregiously wrong.
Okay.
And it kind of it's rooted in sort of the same ideas of, because the majority thinks it right, it must be right, which is just not true.
This is actually the argument for open source.
Okay.
This is. I'll let Linus know about your disgruntlement with his comments.
No, I think that it's fundamentally, it is a good idea that the more people you have looking at something, the more.
Well, this was the argument for open source versus closed source, like hiding implementation details and exactly what you just said.
Mm-hmm. Yeah, I think what I was talking about is less the objective and more the subjective. And so with the objective facts of this code doesn't work, I think absolutely. But when there's always going to be subjectivity in design and especially in like modeling and whatnot. And so I think that's where that starts to break down, because you can have differences of opinion, amongst experts.
Yeah, I mean, what if you put the source first before the destination, or the destination before the source, which we ran into in C library stuff? I mean, two sets of experts just chose two different ways of doing it. And so two different libraries. I'm always looking at the manual pages because, I mean, both were reasonable. Like it's, you can't really say that one's right and one's wrong in that case.
Yeah. So I think that what you're getting at is, for ironing out execution in a lot of ways, the more people we have looking at this and inspecting it and caring about it, the more likely it is that we're going to find those problems. But when it comes to areas of subjectivity, that's where you kind of have more issues, because there could be two equally good ways of doing something, and two people or two groups of people could argue about it till the end of time.
Yeah.
So I think it's important also to distinguish between the design and subjective kind of components of writing software, and then the objective sort of, is it actually doing what you think it's doing? Is it running?
So Nathaniel brings up an interesting point to that, which is this notion of formal verification. It is, there are techniques to basically prove that something does what it says it does under all inputs. There are, I can tell you that a lot of these techniques are extremely costly in terms of like human resources, and that generally means in terms of time. There are mathematical proofs you could give to say, like, this is correct. This is provably correct code. C is not one of those languages that likes to lend itself to that. But there are languages that are actually built entirely on that like premise.
Okay.
But we're learning C. So I'm giving you naked pointers, and you can do whatever in memory, and like you could take a void pointer and turn it into a pointer, and then decide to change it to a char pointer, because you feel like it. I mean, it's
not even like a formal verification thing though. It's and it doesn't need to be absolute proof or something. It's that I think that a certain degree of skepticism is always healthy, and the further away
the trolls
you get
are out
from
now, big time, because
what you think the standards are, the more dangerous it gets, especially if it's just Joe Schmo at your company has written this code. Like,
yeah, Joe has to be watched. Yeah, you got to watch Joe. But
yeah, that's what I'm saying.
Yeah, you got to have standards.
I've seen too much code handed down to project managers and whatnot.
I don't trust Joe.
Aren't technical at all, and just go, oh, it works. Oh, you've thrown some numbers at me, and its accuracy is what? Oh, cool. All right, sure, we'll package this up and sell it. And then somebody comes along a couple years later, opens it up, and is like, what the heck is this? Like, that has been way too much of a component of my job for me to just go in and trust on faith that things do what they say they're going to do.
They say that's why they pay you the big bucks. But to Math's comment, I actually missed this earlier. I feel like the header files are like the instructions for your instructions in a way. Have you encountered a situation that you had to create like your own headers for the code to work with the way you intended? Yes, Math, that absolutely does happen occasionally. There's all sorts of screwy, like sometimes like the definitions are no good. I usually try to find another library at that point rather than go through the trouble of like really like what code is really worth it. Like if they like solved the P equals NP problem in there, like, okay, I'll bother to figure out like a decent header for that. But like it, your normal run of the mill computer science object, it's like there's usually another library, there's usually a better option, and and the trolls are just out in force right now. So like there's a lot of languages that they're starting to throw around which are much more serious about keeping the programmer from doing harm. They also sometimes keep the programmer from doing any programming. But it sort of depends what you want to trade. Like, do you want to trade correctness? I mean, like COBOL's pretty solid for that. You can really verify that like the given inputs and the output. I mean, it's like pretty straightforward, that's anyway. We can go down that path. I think that's I think we're basically in the discussion. So before I wrap this beautiful code editor that we built up, is there any is there anything I missed that you're like upset? Oh my God, you didn't mention that. This is just not a C course. Okay, fair enough. So, but I mean, like, is there something someone told you about that you were like, oh man, I was really hoping to learn about blah?
Nobody I know except Dennis knows C.
Okay.
Actually,
Guy, how could you not show the union? Like, I didn't show the union.
I thought you would love this. So I'm hopefully this won't get too much. I know we need to like officially sort of transition into the storytelling time, but I cannot believe I forgot to tell you this. So.
Wait, if this is a story, then we're transitioning.
Oh, okay, all right. I'll wait then. I'll wait.
No. I mean, we'll transition right now. I'm just saying, like, I think that's. Okay. Hold that thought.
Okay, I'll hold it.
Okay, you got it. I don't think there's any other. I think we're good. I mean, chat. Is this? Keep me honest here. Is this a legit version of C as an additional language? I want to hear your comments. I want to hear your feedback. Actually, I don't want to hear too much feedback.
Some honesty, but not too much. What is it from Interstellar? Like honesty 90% or something?
Yeah, okay, go honesty 90%.
I think it's hard for me to ask questions because of the things that you've shown me, I feel like I understand them. I agree with you that I want to practice things a lot more.
Yeah, I think that's the biggest failing so far in this course. That's on me. I just got to build a version of multiuserpad. But
I think more projects and practice is always good because I ran into this problem with Python when I was first trying to learn it, that I watched so many videos and read so many articles on how to do stuff, and I just was like, why am I not getting it? Because that's how I learned a lot of things, is by reading the textbook. And then it really just, I exponentially grew as a programmer when I started just writing Python every day.
Oh, sure.
And so I think for me,
I think there's no question
having
about
learned
that.
that lesson, I want to continue
Yeah, no, I do
by
too.
practicing.
I'm gonna wrap like the CA3L up. I think we can call that. I think we can call that a course. I mean, next I would definitely like doing it again. I would definitely add that in the whole having a better practice place, having a place where like you can easily work.
Mm-hmm.
I do kind of like to what Nathaniel's bringing up now. And by the way, I do agree that that's a reasonable exercise. I'd say that that's not necessarily part of the C course. Part of why I went after this multi-user pad was because we didn't have to get involved in any environmental setup. There's no system setup. There's no updates. There's
Yeah.
no we just jump onto a web page and we're coding. Like we don't have to worry about any of it. And that's sort of by design. Like I wanted to focus on C more than like tool chains and
It
compilers and
would
stuff
be
like
good
that.
to kind of have a, first time setup type
Yeah,
thing.
yeah.
But
Well, we could go do that. I think that's a good. You know what? Let's do that next time. Let's actually make
okay.
that the next.
Yeah.
I'm not going to call it part of the C class, but that we'll go in and up. We'll do a shared I'll spin up an instance on EC2, and we're just going to go from this is scratch hardware. How's that sound?
Sounds good.
All right.
I
don't
need
want to
know
do
how
Linux
like,
from
practice
scratch.
things,
We're not gonna build the kernel to start the system. But
no taking over what Last Miles does.
That's all right. So we'll say for the next stream we'll do configure an EC2 instance. All right, that's cool. I'm down with that. Let's see and catch up. Oh, cool. All right. Well, it seems like and the project CCVE we're moving into the project.
What
next.
we're working on, yeah, scoping that out right now.